Back and better than ever. It's time for another weekly recap video here on Mr. Wilson Teaching. This week we talked about special right triangles and trigonometric ratios. We're going to jump right into special right triangles. We'll talk about the 45-45-90 triangle and the 30-60-90 triangle, and then we're going to make a flow chart. The 45-45-90 triangle gets its name from the angle measures. Notice that these angles are both 45 degrees. The significance of this is that if we have two congruent angles, then the sides across from those angles must be congruent as well. So I'm going to mark these sides congruent and say that they have length L for leg. That makes this an isosceles triangle. This side is a hypotenuse because it's a right triangle. So I'm going to say it has length H for hypotenuse. Because it's a right triangle, we can use the Pythagorean theorem to put H in terms of L. So our original Pythagorean theorem is c squared equals a squared plus b squared. The hypotenuse always goes where c is, so I'll replace that with an h, and I'll replace a and b with l's. Well, L squared plus L squared can be rewritten as 2L squared, and we can take the square root of both sides to get h by itself. The h squared and the L squared can come out of the radicals as just h and L, but the 2 doesn't have another 2 inside, so it stays under the radical. So we have h equals the square root of 2 times L. So in a 45-45-90 triangle, the length of the hypotenuse is the length of the leg times the square root of 2. An example where you might use this is shown here, where it says to solve for x and y. The legs are congruent, so x equals 5. The hypotenuse is just the leg times the square root of 2, so we get y equals 5 square root 2, which doesn't reduce. In that example, we were given a leg and asked to find the other leg and the hypotenuse. In our next example, we're given the hypotenuse and asked to find the two legs. Again, the hypotenuse is just the leg times the square root of 2, so let's fill in what we know. The hypotenuse is 18, and one of the legs is x. So 18 equals x times the square root of 2. If we divide both sides by the square root of 2, we end up with x equaling 18 over the square root of 2. It's not good form to leave a radical in the denominator, so we're just going to put it in our calculators and get 9 square root 2. I won't waste any of this video explaining how to simplify radicals, but if I get enough requests in the comments, I'll make a separate video walking through that. For now, just know that on an exam, you'll be allowed to use your calculator to reduce it. Back to the problem. Since the legs are congruent, y is equal to x, so y also equals 9 square root of 2. Next, we'll cover the 30-60-90 triangle, which I want you to think of as half of an equilateral triangle. Watch what happens when I cut this down the middle. The 60-degree angle at the top gets split into two congruent angles which must measure 30 degrees. When I split the bottom side in half, it results in two sides that are half of what the original was. That's why I made the sides 2x instead of just x, by the way. So that's where we get 30 degrees and 60 degrees from, and the third angle, if we do the math, has to equal 90 degrees. So the hypotenuse is twice as long as the short leg, and we can use the Pythagorean theorem to find the long leg. Again, c squared equals a squared plus b squared. I'll replace c with 2x, replace a with x, and I'll label my long leg y for now, and I'll put that in for b. Notice that I put parentheses around 2x. We want to remember to square the whole thing, not just the x. When we do that, the 2 becomes a 4, and the x becomes x squared. I can subtract an x squared from both sides to get y squared by itself. And now I can rewrite the left side of the equation as 3x squared. I'll take the square root of both sides, and just like before, the things that are squared can come out of the radicals, but the 3 has to stay in. So what we're left with is the longer leg equaling the shorter leg times the square root of 3. Let's see this in action. Again, we're solving for x and y, and we're given a length of 11 for the short leg. The longer leg is the shorter leg times the square root of 3, so x equals 11 times the square root of 3, which doesn't simplify any further. To get the hypotenuse, we just multiply the shorter leg by 2, So y equals 11 times 2, which is 22. That time they gave us the short leg and asked us for the other two sides. This time they give us the hypotenuse and ask for the other sides. We know that the hypotenuse is just the shorter leg times 2, so in this example, 6 equals x times 2. Divide both sides by 2, and x equals 3. Now that we've found the shorter leg, we're going to multiply it by the square root of 3 to get the longer leg. 3 times the square root of 3 cannot be reduced, so we leave our answer as y equals 3 square root of 3. Lastly, here's an example of them giving us a long leg and asking for the other two sides. The longer leg is the shorter leg times the square root of 3, so 30 equals x times square root of 3. When we divide both sides by square root of 3 to get x by itself, we're left with x equals 30 over square root of 3, which simplifies to 10 square root 3. If you want an explanation of how we simplify these radicals, a link to that video will appear here, if and when I ever get enough requests to actually make that video. Anyway, the hypotenuse is the shorter leg times 2, so we'll just double our previous answer and get y equals 20 square root 3. Let's build a couple of flowcharts to help us remember what steps to follow on each of these problems. For a 45, 45, 90, I have a hypotenuse and a leg, and they're related by the square root of 2. If I have the hypotenuse and I want the leg, I'm going to divide by square root of 2. If I have the leg and I want the hypotenuse, I'll multiply by the square root of 2. For a 30, 60, 90, I have a hypotenuse, short leg, and long leg. The hypotenuse and short leg are related by 2. If I have the hypotenuse and I want the short leg, I'll divide by 2. And if I have the short leg and I want the hypotenuse, I will multiply by 2. The short leg and long leg are related by the square root of 3. If I have the short leg and I want the long leg, I have to multiply by the square root of 3. If I have the long leg and I want the short leg, I have to divide. Now honestly, you could stop the flowchart here because even though I haven't drawn a line connecting the hypotenuse to the long leg, there's still a path between them. You could get from the hypotenuse to the long leg by dividing by 2 and multiplying by the square root of 3. And you could get from the long leg to the hypotenuse by dividing by the square root of 3 and multiplying by 2. But if you wanted to do it all in one step, you could multiply or divide by square root 3 over 2. I didn't draw this step on any of the worksheets I did on the screen in class, so there's no reason you have to. I just put it on here to show you that in these two types of triangles, you can find any side length from any other side length in just one step. And that is what makes them special right triangles. Our other topic for this week is trigonometric ratios. We're going to briefly talk about what a trigonometric ratio is. We'll define sine, cosine, and tangent. I'll give you some mnemonics to remember them, and then I'll show you a few example problems. A trigonometric ratio is just a ratio of two sides of a right triangle. One of the key words here is right. For our purposes, it has to be a right triangle. The three that you need to know about are sine, cosine, and tangent. We abbreviate them as sin, cos, and tan, but even when they're abbreviated like that, we still read them as sine, cosine, and tangent. Kind of like how you don't call me M.R. Wilson. You know that M.R. is an abbreviation, and you read it as Mr. Another term we're going to throw around for the rest of the unit is reference angle, which is just the acute angle used when calculating the ratio. Keyword in that one would be acute. The right angle is never our reference angle. And if we have a right triangle, we don't have an obtuse angle. Now, if those trig abbreviations from a minute ago sound familiar, it might be because you've noticed them on the school calculators. There's a button for sine, cosine, and tangent. Before we define trig functions, we need to talk about some notation that we're going to use. The definitions will include a Greek letter theta, which I want you to think of as being like x. By convention, we use our normal letters for variables that represent numbers and lengths, and we use Greek letters for variables that represent angles. I don't want to overwhelm you, so I'll mainly just use theta, which you can write by making a 0 with a little dash through it. I also want you to see how we read equations that have trig functions in them. I would read this as the sine of theta is 0, the cosine of angle B is equal to 1/2, and the tangent of 45 degrees equals 1. Notice for all the trig functions written in green, it's the sine of, the cosine of, and the tangent of. Notice that the second part, written in orange, is always an angle of some kind. It can be a variable that represents the angle measure, like theta. It can be the name of the angle, like angle B, or it can be the actual angle measure, like 45 degrees here. For tangent here, I also included parentheses. You won't see that very much in this class, but the yellow calculators we use in class force you to put parentheses around the angle measure, so I wanted to show you what that looks like. The parts in blue and yellow here shouldn't be new for any of you, so let's move on to our definitions. The sine of an angle is defined as the ratio of the opposite side to the hypotenuse. If I'm looking for the sine of angle A, that means I'm using angle A as my reference angle to determine which side is the opposite side. Here, that would be side BC, which has a length of x. So x goes on top of the fraction here. The hypotenuse is always, always, always the side across from the right angle. So in this diagram, that is side AB, which has a length of z. So in this diagram, the sine of angle A is x over z. The cosine of an angle is the ratio of the adjacent side to the hypotenuse. We're going to use angle A as our reference angle again, but what on earth does adjacent mean? That may be a new word for some of you. Well, in everyday English, it means next to or touching. The geometric definition is a little more precise. It has to do with sharing a vertex, but the idea is still the same. We just want a side that touches angle A. As you can see, there are two sides that meet at angle A, so how do we decide which one we call adjacent? We're going to pick the one that touches the right angle, so in this case, side AC with length y. We pick that one because the other side touching A is already the hypotenuse. So cosine of angle A is y over z. That just leaves us to talk about tangent. The tangent of an angle is the ratio of the opposite side to the adjacent side. Again, if my reference angle is angle A, then side B is my opposite side, which has length x. So x is going to go on top of my fraction. My adjacent side, again the side that touches A and isn't the hypotenuse, is side AC, which has length y. So the tangent of angle A is x over y. Here's the fun part. Let's talk about how to remember which trig function is which. The tried and true mnemonic for trig is SOHCAHTOA. Basically, every trig mnemonic is some form of SOHCAHTOA. It's meant to remind you that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. The way that I normally write it is by putting SOHCAHTOA in a 3x3 grid. Then I put equal signs between the first two columns and division signs between the last two columns. And if spelling isn't your thing, there's even a bunch of mnemonics to help you remember how to spell it. One of my favorites is some old hag clipped all her toenails outside Aldi. There are many, many others, some of which are highly inappropriate and you'll never hear from me. But if you happen to Google them yourself, I can't stop you. The great thing about this mnemonic is it doesn't just tell you which sides go with which function, it tells you which order the sides go in. To illustrate why that's important, we're going to have to look at something I couldn't show you in class. Something so shocking, so vile, so beyond the scope of Oklahoma's academic standards for high school geometry that I can only call it dark trigonometry. For the slide I'm about to show you, parental discretion is advised. You know what? Grand parental discretion is advised. So if you're under the age of 55, you should probably get someone with an AARP membership to watch with you, or just skip to the next chapter. Okay, here we go. On the left, we have our regular basic trig functions. We have sine, which is opposite over hypotenuse, cosine, which is adjacent over hypotenuse, and tangent, which is opposite over adjacent. Mr. Business Grandpa gives these a thumbs up. But on the right, we'll see what happens if you get the sides in the wrong order. If you put hypotenuse over opposite, that's not sine anymore. That's cosecant. If you put hypotenuse over adjacent, that's not cosine anymore, that's secant. And if you put adjacent over opposite, that's not tangent, it's cotangent. These are all valid trig functions, but they are not the ones you'll be using in this class. Mr. Business Grandpa will be mad at you if you use cosecant and call it sine, or if you use secant and call it cosine, or if you use cotangent and call it tangent, or if you drink Pib and call it basically Dr. Pepper. Okay, maybe I'm the only one that'll get mad about that last one, but still. That's it for the scary part. You can open your eyes now. Let's see these functions and the mnemonic in action. Our next example says to use the diagram shown to find the trigonometric ratios. So we're going to find the sine, cosine, and tangent for both angle D and angle F. To help you follow along, I've put a SOHCAHTOA in the top right corner. Let's focus on angle D first. To find the sine of angle D, we need the ratio of the opposite side to the hypotenuse. Here, the opposite side, in blue, has a length of 8, and the hypotenuse, in purple, has a length of 17. So the sine of angle D is 8 over 17. Cosine is adjacent over hypotenuse, so for angle D, cosine is 15 over 17. Lastly, to find tangent, we need the opposite and adjacent sides. Again, the opposite side in blue has length 8, and the adjacent side in red has length 15, making the tangent of angle D 8 over 15. Now let's make angle F our reference angle. Notice that with F as our reference angle, now our opposite side is side DE with length 15, but our hypotenuse doesn't change. It's very important to remember that opposite and adjacent both depend on which angle you're referring to. So anyway, the sine of angle F is 15 over 17. That's odd. The sine of angle F seems to equal the cosine of angle D. Probably just a fluke. Anyway, for the cosine of angle F, we're going to use the adjacent side in red, which is 8 in this case, over the hypotenuse, which is still 17. So the cosine of angle F equals 8 over 17. And that seems to exactly equal the sine of angle D. I wonder if there's any significance to that or if it's just a coincidence. Foreshadowing is a narrative device in which a storyteller gives an advance hint of what is to come later. Tangent of angle F is 15 over 8, which is the reciprocal of the tangent of angle D? Weird. For the next type of problem, we're going to need our calculators. If we know one of the acute angles and one of the sides, we can use that information to find another side following a 5-step program. Using the given reference angle, label the sides as hypotenuse, opposite, and adjacent. I would label them in that order because hypotenuse never changes and opposite is easy. Then when you label adjacent, there's only one side left that it could be. Step 2 is determine which trig ratio should be used. Then you'll set up your equation, solve it for x, and use a calculator to find a decimal approximation. I'll show you how to use the yellow calculators for this, as well as how to use the iPhone calculator app for it. Our final example says to find the value of x and round to the nearest hundredth. Our first step is to use the reference angle, 67 degrees in this example, to label the sides as hypotenuse, opposite, and adjacent. The hypotenuse is always across from the right angle, so we can label that one first. Next, we'll label opposite, which is across from our reference angle. And then, by process of elimination, the adjacent side is the one with length 4. The next step is to determine which trig ratio we can use. We don't have any kind of label on our hypotenuse, no number, no variable, so we can't use any ratio that uses the hypotenuse. Looking at my SOHCAHTOA, that leaves tangent as the only one that we can use. So now we're going to set up our equation. I always start by writing the definition. Tangent of theta equals opposite over adjacent. Then I can fill in what I know. Theta, our reference angle, is 67 degrees. Our opposite side is x, and our adjacent side is 4. Now that our equation is set up, the next step is to solve for x. Here, that's as simple as multiplying both sides of the equation by 4. So x equals 4 times tangent of 67. Now we're going to use a calculator to find the decimal approximation. On our classroom set of yellow calculators, you're going to just type it in from left to right. So 4 times, then when I press tangent, notice that it automatically puts an open parenthesis. That's why I showed you that notation a billion slides ago. I type 6, 7, closed parenthesis, enter, and it gives me 9.4234 something. Because the problem says to round to the nearest hundredth, we're going to write 9.42. If the next digit had been a 5 or higher, we would have rounded up to 9.43. Also, I didn't have to press the times button. I could have just done 4 tangent of 67 degrees and it would calculate the same answer. I also want to show you how to put this in your calculator app. I have an iPhone, so that's what I'm going to use to show you here, but Android is similar. We're going to use landscape mode so that we have a scientific calculator. We first find the tangent of 67 degrees by typing in 6, 7 and pressing the tangent button. Now we can multiply that by 4 and get the same answer we got a minute ago. X is approximately equal to 9.42. So that's week 9. We are halfway through the semester, y'all. Remember to smash that like button, subscribe for more weekly math content, and all the other YouTube things that sound cringy coming from your math teacher. Or just don't. I get paid the same either way. Unless Quick Trip sponsors me. Well, words are hard. Can comes out of the radicals. I can't type either. I can't talk, I can't type. Well, in the denominator, this one's gonna have a blooper reel at the end. I'm calling it now. Split into 2 congruent angles. Lost my place in the script again. I'd lose my head if it wasn't screwed on. Mr. Business Grandpa give these a thumbs up. I can't write a script to save my life. We'll see what, To find, okay. Gross. Foreshadowing is a narrative device. I can't read it when I hold my microphone right there. Kind of label on our hypotenuse. Hippopotamus. Dark trigonometry. Dark trigonometry. Maybe add an echo.